Hi, I'm Tessa. I am a research scientist at Databricks. Before that, I was working at a startup that got acquired by Databricks last year. So I went through that transition from small startup to big company. Before Mosaic, I was at the New York Times doing sports photography. And before that, I was working in various data science roles at Snapchat, SpaceX, and Tinder. So this talk, I will be talking about a large language model trained by Databricks this past spring. I'm going to try to convince you that our model, DBRX, is a good model, but more importantly, I'm going to try to convince you that training large language models is becoming more and more accessible and affordable. You can do it with a small team. The cost is coming down. Second of all, there's a lot of data science tie-ins with large language model training. If you like data science, you're going to love large language models. And third, and this is a little controversial, I'm going to try to convince you that it's really fun to pre-train. So this is the agenda. I'm going to talk about DBRX and the architecture. Then I'm going to talk about the evaluation. Importantly, DBRX is an open source language model, so you can download it to your computer, and if you have a really large computer, you can run it. I'm going to talk about efficiency for training and inference and how you can try it out for yourself. And throughout this discussion, I'm just going to mostly focus on the process we went through to train it. So DBRX has two components. One is the base model, and the other component is the instruct model. The base model is what is the result of pre-training, and the instruct model is the result of fine-tuning the pre-trained model. And so you can kind of think of the base model as like a new freshman in college, and the instruct model as like they've graduated, they've learned their major. There's some really interesting relationships between the base model and the instruct model. For instance, like you can fine-tune to an instruct model, but you can't go back to the base model. You like lose capability. Another interesting tie is that the base model takes about 3 months to train. The instruct model takes like 8 hours. So a majority of the computation and cost is coming through the base model, which is very interesting when you like look at the data. So here's a slide, and I don't know if you can see the words, where a person is interacting with DBRX, and the left-hand side is DBRX, the right-hand side is Llama 2. This slide is supposed to highlight the speed of DBRX, which was achieved through like architecture innovations that Llama did not have. And so you can see the tokens are coming out faster on the left. And just so you know, for this talk, a token is like a subword that is like the fundamental pixel for language models. So I'm going to now try to convince you that it's a pretty good model. So here is our comparisons against other open source language models. These are the big three currently tests for large language model capability. They're MMLU, Human Eval, and GSM-8K. MMLU is like a combination of the SAT and MCAT and pretty much a ton of multiple choice questions. It's really hard. When I take MMLU, I get like 50%. We're getting like 73%, so it's better than me. Human Eval this is funny, it has nothing to do with humans. It's actually a coding eval where the model is forced to finish writing a small Python program, and then we run that program and see if it works against some unit tests. So we do much better than other open source models on human eval. And the last one, GSM-8K, is K through 12 math problems. So not data science or stats problems, but like grammar school math. And as you can see, we're doing pretty well against Llama and Mixtral and Grok on programming and math. Here's another graph that shows our performance against some other open source models. This is our head-to-head comparison against GPT 3.5, which is not the current best version of GPT. You can see that we're beating them on human eval and GSM-8K. They are closed source models, so researchers can't download the weights. Here's another graph showing, oh, and I thought this was so funny in this audience. It's really terrible that we don't have error bars on any of these graphs. And the reason that we don't have error bars is that there's actually not a standard way to calculate variance for these scores yet. So that's what we could use from the data science community. So math experts can come teach us how to make our error bars better. This is another plot without error bars showing us having high common sense and being truthful. So for 2 glorious weeks, we were the #1 open source model in the world, and then Llama 3 came out. So that was kind of the sad end to this story, but the most valuable things we got out of it were the lessons we learned along the way, which is what I'm going to talk about next. Llama 3 was smaller and not sparse. We are trying to market this model to enterprises that want to customize and pre-train on their own data. Next, I'm going to go through the architecture. So DBRX is a transformer-based decoder-only large language model that was trained using next token prediction. It was trained entirely from scratch, which means that all 132 billion parameters started out with a random number, and then over the course of 3 months, those got assigned their final values. It was pre-trained on publicly available data sources, so no customer data, just Common Crawl, essentially, which is a large public scrape of the internet. And it was trained on 12 trillion tokens. And here it says that these 12 trillion tokens were carefully curated, but I think that's a pretty loose statement, because if you look at the training data, it's not what you'd expect. It's a lot of random news articles and blogs from the early 2010s, which is sufficient for learning English, but it's not really what you'd expect from carefully curated data. So to get a sense of what 12 trillion tokens is, by the time you're 30, if you read 30 pages a day, you've probably seen 1 trillion tokens. So it's not that much text, but it is a lot to store on a computer, and it does take a long time to optimize over that data set. The context length here is 32K tokens, and to give you a sense of how large that is, the popular young adult novel Twilight is 100,000 tokens. So this is every time a language model answers a question, it can usually see about a third of Twilight in context, which I think a lot of people don't take advantage of when they're asking questions. So you can write a very long question with a lot of context, and that only provides more information to the model. And my current research area is extending that context length even further to 100,000 or 1 million tokens, which sounds wild, but it is possible, and other models have done this. We estimate that our tokens are 30% better than previous tokens, which is very good. And we have a ton of data scientists on the data team analyzing our training corpus and improving it, just because it's not humanly possible to curate 12 trillion tokens. Something that might be interesting to this crowd is that we used curriculum learning for pre-training, which is, I don't know if it's totally based in optimization theory, but basically as you train it, you start out with basic text and you evolve it to be more and more complicated. So you add in code and math towards the end of training after you've learned English and learned a lot of basic, I guess, representations. And we had some interesting research on curriculum learning from our data science team, which was that for language, you only need about 3 billion parameters to get a pretty good score on some language metrics, but you need at least 7 billion parameters to get a good score on code and math, which is kind of an interesting finding, and it kind of suggests that math and code are actually more difficult than basic English. At least that's a stylized version of that result. Our model was trained on 3,072 H100 GPUs in San Jose in a data center. This took about 3 months, and it was many tears were cried in these 3 months by me and others. So 3,072 GPUs run extremely hot, so they're like 100 degrees. They are running, and they are so loud that if a data center employee needs to go unplug one, the employee has to wear ear protection to protect themselves from like the incredibly loud noise they make. And because they're running hot and loud, they fail fairly frequently. And we have some software that our engineers have built to adapt to the failures. But like once a night for like 3 months, we would have to get up and debug the cluster because we would lose too many nodes to failures, and we'd have to reallocate our resources. And this was just the most arduous process I have ever experienced, because every moment that the run is not training, every minute it costs $150. So this is incredibly high stakes debugging, and sometimes we were down for like an hour and just trying to figure it out. This was a very painful process, but it really like taught me a lot about computer hardware and switches and topologies. So it's a learning process. And by the end, we were running very smoothly, I would say, like after we realized all of our mistakes. And some of the mistakes are not what you'd expect. For instance, like when you upload your data to AWS, it seems like a process that does not require like a PhD in computer science to understand. It's like, well, just download the data. A lot of our bugs were related to downloading from a cluster in the cloud and being like essentially DDoSing the cluster, and we'd get rate limited, and then the run would go down. So that this was like, that's kind of like some of the stories from training the model. Here's the importance of high quality data. So more into the architecture, and this is specifically related to the speed of decoding. DBRX is a mixture of experts model. A standard non-mixture of experts is referred to as a dense model, and a mixture of experts is a sparse model. So it is in total 132 billion parameters, and when it was training, those were the number of parameters we were adjusting. But when you run inference, only 36 billion are used. So it's kind of like a dolphin that like sleeps half of its brain at a time. It's not totally like that, but you can think of it that way. And so we used a dropless implementation of a mixture of experts from an open source repository called Megablocks. We also used a smaller number of experts. Each layer of the network is divided into like 16 experts, and for each input, the network at inference time dynamically chooses which 4 of the experts to use. So in a transformer, the attention, which we were told is all you need, the attention layers are actually pretty computationally cheap, but the feed forward layer after attention is incredibly expensive. So a mixture of experts model tries to get around that by only using these 4 of 16 experts. Each expert is like a feed forward layer at a time during inference. And the reason this matters so much for inference, and I didn't realize this when I started out at Databricks, which is that when you're decoding, you're doing so in an autoregressive manner. So that means that for every new token, you need to do an entire forward pass from the model. So this really limits like the top speed you can go for decoding. And as we know with customers, speed matters so much. So that's why we ended up going with this mixture of experts implementation. Other cool things we used during training and inference are the rope embedding, which is during attention, a lot of information is lost. The most important piece of information is lost is what order of the words are in the sentence. So rope provides an extra layer of information about where the position of the words are in the sentence is. It's actually very interesting. It's like based on a clock face. If you look at this paper, it's pretty fascinating. Another interesting thing we use were gated linear units and group query attention. We used the tokenizer called TickToken, which is my favorite tokenizer because of its name. One interesting fact about TickToken is that there are no tokens for each of the numbers, so the model cannot learn to do math in a kind of normal way because it doesn't have a representation of individual numbers. It like tokenizes all of pi together, not all of pi, but like subset of pi together. So it has to like pretty much memorize different math concepts that you can just use an algorithm to do. So that was one mistake, and I think we would change that if we were to do this again. These are some tweets about the architecture that I'm not totally sure are relevant. We used our own software stack for DBRX. We have our own like open source training library and our streaming dataset library and our LLM library. And what I currently work on is the evaluation library because that's like it's the most fun thing to work on. We are like definitely hiring for all these types of teams if you're interested. We also have like a lot of data inspection tools, for instance, Lilac, notebooks, Unity Catalog, multi-cloud training. Multi-cloud training, I don't know if that's, yeah. And MLflow for experiment tracking. But for DBRX, we used weights and biases, mostly for telemetry and monitoring. We also used these open source libraries, PyTorch, Megablocks, and TensorRT. TensorRT is for inference. VLLM is also for inference, Eleuther, and AI2, which is here in Seattle. We actually got most of our data from AI2. So I have a bunch more slides, but I could skip ahead of these ones. So there is a special, I'll just go into like long context evals because this is my favorite thing to talk about. So it's actually really hard to measure model performance. Most of the time, people, when they are looking at models, they just pick the one that has most people pick the model that has more formatting and longer, but this encourages kind of chatty and talk too much for most business needs. So we've been working a lot on how to evaluate like long context. So there's like a bunch of databases of legal documents and stories and like movie transcripts that we try to get the model to summarize or answer questions about. Let's see. Here are some other evaluations, and when you see 5-shot or 10-shot, that means the model gets like 10 examples of what the question looks like ahead of time. So it's not really something that has a good human counterpart because we don't really need it. But imagine if when you're taking the SAT, you get a bunch of like 5 pre-answered SAT questions ahead of time that give you a clue about what you're supposed to do. So it's kind of like learning from example, and this is called in-context learning. And there's some like, we start to like, when we have long context, if we're going to do in-context learning, if each prompt has like many different, like if you have a bunch of legal documents and you're trying to give a model examples, you need a much longer context to do multi-shot in-context learning. Another task we really emphasized with DBRX was retrieval augmented generation, which is really hot right now because you can be an organization with a bunch of documents and you can take a pre-trained model, and the pre-trained model learns like the embeddings of the documents, and you ask it a question and it can use those embeddings to find the answer itself, so there's no training involved. This is like a pretty lightweight way to use a pre-trained model for your own business. And there's a theory that this will prevent hallucinations, because if you have access to the manual, you don't necessarily have to hallucinate the answer. In practice, we're still figuring out how to even measure hallucinations, measure correctness of answer. There's still so many open questions about retrieval augmented generation. Yeah, we could go into efficiency, but does anyone have any questions? Because I don't know exactly what people are interested in, so yeah.
I can just ask that. I was just wondering about those percentages, in terms of evaluating what is outperforming the other, like the person something. How do you normalize examples of performance of ChatGPT to DBRX for specific categories?
Let me find a good example.
Was it that the data that you used, and did you use the same data, or?
So it actually depends on which evaluation metric we're talking about. So for MMLU, which is like the SAT, it's a standard. We have a gold answer. It has to give an answer A through B. And we actually look at, well, this is too many details, but you can either look at the logits of which A, B, or C, or D is getting the higher probability, or you can ask it to just output the token, and that adds a little bit of noise. So that's one kind of decision you have to make as an evaluator, whether you want to use the logits or the actual output. For other evals, like human eval, we actually execute the code that ChatGPT outputs versus what we output. And if it passes 3 or 5 unit tests, then we give it 100%. Human eval is a very central but kind of suspicious metric, because there's only 192 questions. So that's incredibly sensitive to getting one question wrong. And I think a lot of people don't pay attention to the outputs the model are giving. So if the model slightly misformats the code, I don't really believe that you should give it a 0. So we spent a lot of time making sure we were giving a fair evaluation for human eval. And another problem is if you only have 192 questions, there's a significant problem where a lot of the test data is in the training data. So we have to make sure that doesn't happen. Otherwise, it's just memorized results.
And then have one more relevant question, but I'm happy to Oh yeah. So you mentioned something like we can curate that data. Is Databricks also curate data themselves, or did you do whatever ability to curate data?
We used data we used a mixture of sources. So one came from AI2 here in Seattle, and they did deduplication and they did removal of toxic content. That was the level of curation they did. So there's no person who's gone through all of this and looked at it, which is disturbing, but it is 12 trillion tokens, so it's a lot. But for math and computer and code, we really looked through that a lot because it's so important. So what we would do is we take a representative sample and just make sure that it passes some checks. I mean, it's really, we could use more data science methodology in our data curation.
Did you do any sort of guardrailing to prevent hallucinations during your training?
To prevent hallucinations, no, we did not do guardrails for pre-training. We do guardrails for illicit content generation for our API, but that's the only level of guardrails we did. We didn't do red teaming or more advanced guardrailing.
Hi, I have a question that's not quite as technical, but I was wondering, a lot of the stuff you're talking about sounds like teaching humans. So I was wondering if you have any experience, or if you know from more of the background of this, has this been informed by education of like people at all, or
I think
do you guys think about that at all?
Curriculum learning does not have a strong basis in optimization theory, but it has a strong basis in human optimization. So I think that's why we kind of considered it at all. I would say, like, there's not really a good analogy between training language models and training humans, because when we took a sample of the model halfway through training and started generating outputs from it, we could not believe how good it was. Like, none of us expected it to talk as well as it did. And so I don't know if that happens with humans, that you're just so shocked by your student after taking it out of the learning center. But maybe it does. I haven't.
Hi, I have a question. Did you, for the inference efficiency, did you guys use KV cache or stuff like that to make it fast?
Yeah, we used KV cache. We have done a lot of research with actually quantizing the KV cache, and that has a significant impact for like long generations. Yeah.
Another quick question is, so how do you think about like I know you said that you eval the base model versus the instruct, and the instruct actually have some catastrophic forgetting kind of thing. Like, do you think the mixture MOE actually addresses that, or you think that's still?
Yeah, we don't have a good theory about whether MOE causes more catastrophic forgetting in fine tuning. It kind of makes sense that it would, but I would have to see, like, there's constantly results that become intuitive after you see the result in this field. So we should definitely look into that.
Okay, I don't think we have any more time for questions, because it looks like the next group is coming in. So thank you very much, everybody. Thank you, Tessa.